Students of the day, my name is Prasad Prabhu and today we'll be discussing something really important in thermodynamics, that's amount of mechanical work done in a reversible isothermal process of an ideal gas. What exactly is a process? When you have continuous changes happening in series, it's a process, and a process has two very important steps or stages. One is the initial stage and one is called the final stage. The initial stage is basically the stage where the process has just started, and the final stage is the stage where the process has just ended. And the major requirement for the process to take place is energy difference. If suppose I say that the energy at initial stage is equal to the energy at the final stage, that means delta E is equal to 0. That means energy difference is 0. That means there's no change occurring. Changes occur only when there is a difference in energy level, due to which there's chemical kinetics. So let us not discuss about that part of physical chemistry. Let's come up to a very important part about change. Now, whenever there's a change happening, there is work being done. And today we'll be calculating how much work is being done when you have a system. What basically is a system? You have been listening to it since a very long time. This is a container, this is not a system. Until and unless I put some amount of gas inside this doesn't become a system. When there's amount of gas inside this becomes a system. So talking about types of systems, you have attended so many lectures, so we'll not get into that. So let us get into the very important part. So when I talk about an ideal gas is an obedient kind of gas who listens to all rules. There are so many rules given by so many scientists. You have Boyle, you have Charles, you have Avogadro. So all of these rules are obeyed like an obedient student by a gas called ideal gas, which is rare. So when we talk about ideal gases, or when we talk about gases basically, we need to remember there are very important three parameters of a gas. One is the pressure of a gas. Pressure of the gas is pressure exerted by the gas on the walls of the container. Second comes the temperature. Temperature is basically the temperature of the gas. And third is the volume. Volume is the amount of space occupied by the gas. So these are the three very important parameters, and based on these parameters you have all your gas laws. So keeping one of the parameter constant, you can find the relation between two other parameters. Similarly, what Charles did was, gave his isochoric law. Isochoric law means he kept pressure is equal to constant, and he knew that the number of moles is equal to constant. Now what exactly did he do? He took a container, he put a piston and he took certain amount of gas where the pressure is equal to constant. He made sure that the pressure is equal to constant. Next, what he did was he increased the temperature by delta T. What is delta T? A very small amount, very negligible amount. He increased the temperature by delta T. So when he increased the temperature by delta T, he saw some kind of an expansion. Of course, when there's temperature, there's expansion, physics. So when he saw the expansion, he saw that there was a rise in the level of the piston. If suppose the same container, there was a rise in height of the piston by a very small amount, that is delta X. Of course, if there's delta T increase, you can't expect a big increase in volume. You will expect a very small increase or change in the volume. So there is a height difference of delta X. So let us consider the area of this container to be base of the container to be A. We know that the container's area won't change, and we know that the amount of volume, the amount of volume increased is the amount of height into the area. Height into area gives you the amount of volume. So it is dx into A. Let us consider that to be dV. dV means a small amount of volume is increased, of course, because small amount of temperature is increased. Because of the small amount of temperature increase, there's a small distance that is increased, and because of the small distance that is increased, there's a small volume that is increased. So dV is equal to dx into area. Dx into area. Okay, let me just write dx dot area. You're multiplying delta x with area because that's the amount of volume that is increased. So this is what basically Charles did. Now he discovered that, from the 8th standard definition of work done is equal to force into displacement. Force into displacement, this is the 8th standard formula of work. We know that pressure is equal to force upon area, keeping force as the subject, so force becomes pressure into area. And in this process, there's small amount of temperature, small amount of distance, small amount of volume. So the amount of work done will also be very small. So we'll call it delta W. Delta W is equal to pressure into area into, what is the distance increase? dx. What is the displacement that has happened? dx. We know that dx into area is dv. Therefore, dw, amount of work done, is pressure into, pressure will remain the same. Area into dx is dv. So this is the amount of work done in an isochoric process. And from here we will be discovering what will be the amount of work done. That is the minute amount of work done, of course. So we will be discovering what will be the amount of work done in an isothermal process. So when we talk about an isothermal process, consider the same two containers. Okay. Now here what we do is we release the pressure. That means we lift the piston. Now when we're lifting the piston, of course the amount of space occupied by the gas increases. If suppose this is the amount of gas, now the gas is still this level. When I increase the piston or release the piston, I'll see that there's more space occupied. And you know that gas occupies maximum space possible. So let us talk about this part. Now here when I release the space, I see that the volume changes from V1 to V2. Volume changes from V1 to V2. Volume is increasing. Pressure is also decreasing on the walls of the system. So let's not just talk about it. In the previous part, we just said that the amount of work done dW is equal to PdV. Okay, this is what we had discussed in the previous session. But that is when we increase the temperature by delta T. That is very small amount. You see all the small amount of work done. But here we have increased by a very large amount, and we know that we just can't find the whole amount of work done by just adding delta W plus delta W plus delta W is big delta W. Of course not. Here you need to integrate. So integrating on both sides. Integrating on both sides. Now when I'm integrating delta W is equal to integration P dV, of course I can't integrate P with respect to V. It's going to be a mathematical crime in chemistry. Let's not just do that. So we have in this picture we have this unique equation called the universal gas equation, which is PV is equal to nRT. Here we need to make P the subject. So P is equal to nRT by V. Substitute this in this equation. Substitute the value here. Integration of delta W is equal to integration of nRT by V with respect to V. Now we have come to a standard integration, but do you think we can just integrate like that? Of course not. We need to add limits because the amount of work done is from 0 to W. And the amount of volume increases from V1 to V2. So the amount of work done is from limit 0 to W, and this goes from V1 to V2. So you have W is equal to, you know, nRT is constant, N is number of moles, which is constant, R is universal gas constant, which is constant, and temperature is constant because it's isothermal. So we get into integration of V from V1 to V2, 1 by V dV. What is integration of 1 by V dV? If you don't know this is going to be very bad. So W, let us keep it as it is because we know it is W. Integration of anything with respect to W is W from upper limit minus lower limit. So it's going to be W. It's going to be W. So this is equal to nRT, natural logarithm, that is to the base E, of V, that is from V1 to V2. So W is equal to nRT log of V2 minus log of V1, which is natural logarithm. We know that by the laws of logarithm, nRT log of V2 by V1 to the base E. And you know it's natural logarithms. To convert it into your base 10 logarithm, you need to multiply it by it. So the amount of work done is equal to 2.303 nRT log of V2 by V1. This is the amount of mechanical work done in a reversible isothermal process when the volume changes. Similarly, what if the pressure changes? We need to find out what if the pressure changes. By Boyle's law, Boyle said that Boyle said that pressure is inversely proportional to volume. Pressure is equal to K by V. Therefore, PV is equal to constant. P1 V1 is equal to P2 V2. V1 or V2 by V1 is equal to P2. V2 by V1 is equal to P1 by P2. So, if suppose I get two pressures, I can say the amount of work done is equal to 2.303 nRT log P1 by P2. And this is how we find the amount of work done when there's a change in temperature, when there's a change in pressure and there's a change in volume.